looking at accumulation of change, which is basically our area under the curve. We talked about how this can help us with total distance, net change, volumes, and overall the algebra or calculus symbol of this is going to be an integral. And so basically our Riemann sums for right now until we get to finding exact integrals are going to help us to approximate that area under the curve. And yesterday we looked at 3 different kinds. We looked at a right approximation, a left approximation, and a midpoint approximation. Now, again, these are an approximation. Or the area under the curve. Now, I do want to go over this notation with you. We talked a little bit again about, remember, Riemann sums means that I'm adding the area of a bunch of rectangles, yes? And what was our notation or symbol that we said means to add up a bunch of things? The summation symbol, okay? So for right now, we're not going to get super far into the technical aspects of our summation notation, but we will in 4.3. Bless you. So I at least want us to start practicing with it because it makes our lives a little bit easier when we get further on. So remember, a summation notation has some sort of variable, okay? For intervals, and for Riemann sums, you're going to see a lot of i's and k's. Okay, those are the 2 most common ones that are used. And your I represents, okay, how many rectangles you're going to use. Okay, so that's what n represents. N represents our number of intervals, or the number of rectangles that we're using. Now remember, when we were looking at this, we're summing together, so that's what that big E stands for, is to sum, and we're summing together the area of rectangles. So what are the 2 things that we need in order to find the area of a rectangle? Yeah, your length and your width, yes? Okay, and we said that, so our base, or the width, okay, how wide each of them were, we can kind of choose that, right? Because we chose 10 because it was kind of a nice, easy number for us. And what we're going to label that as is the change in x. So remember that your delta, which is the little triangle, represents change in x, meaning that those are the widths of my x value. And sometimes you can pick them, but a lot of times the problem will tell you how many intervals that it wants you to have. So to find our change in x, it is b minus a. So a to b is whatever you're going from. So yesterday we went from 0 to 10, divided by however many intervals we want. So yesterday we wanted 10 intervals. We're going from 0 to 10. 10 minus 0 is 10, divided by 10 gave us that 1. Now we just kind of picked that, but sometimes the question will tell you how many intervals that you need, and that's where this little formula comes into handy. So again, we said that represents our width, or our base. How do we find our heights for each of our rectangles? Do you remember? So what did we use to find the height? Did we just pick some random height? No. What did I base my heights off of? The what?
The left or right.
Okay, the left or right point of my interval. Agreed. But then what did I do with those numbers? How did I get 1, 4, 9, 16, 25, 36?
Plug in the function.
Yeah, I plugged it into my function. Yes? So, this was my first rectangle. This was my second rectangle. This was my third rectangle, and so forth. Now, remember that this n represents my number of intervals. It does not necessarily mean that that's the number that we're plugging in. So, in my first interval, right, if I'm using a left approximation, I plugged in 0, not 1. Does that make sense? And so we're going to put f, but it's not going to be of I, because I'm not plugging in 1, 2, 3, 4, however many I want. I'm plugging in x values. Now those x values are dependent upon my interval, because yes, I had to choose either the left or the right of each interval. So that's why it's like sub I, because it's the x value that I need from each of my intervals that we have to go through. Does that kind of make sense? Yes, no, maybe. Now, again, this notation is not going to be especially important while we're just doing Riemann sum approximations. But when we get to definite intervals here after a while, not today, but in the future, it is going to be important that we understand this notation, and we're going to take it a step further. So that's why I at least wanted to show it to you for today. But what did we say our 3 types of Riemann sums were? They were the 3 that we found yesterday. We had a right one. We also had a left one. And we also had a midpoint. So for our right Riemann sum, this is also sometimes called an upper Riemann sum. Our left is sometimes called a lower Riemann sum, or a lower approximation, because again, you're using the upper or higher number versus the lower number. Okay. For our right Riemann sum, we use the right x value. To find our f's of x sub i's, which remember are also our heights of each of our rectangles. For our left, we use the left x value of each interval to find f of x sub I, or in other words, our height. And then here we use the Now remember that yesterday we just averaged our left and our right to find the midpoint, which you can do, but that was because we had already found the left and the right. If the instructions just say find the midpoint approximation, we don't want to have to go through the trouble of finding 2 things that we don't necessarily need. So in that case, we would just use the middle x value for all of them, okay? Now, if for part of the question, kind of like yesterday's, we needed to find the left and the right anyway, then yeah, you can just average them and we would be okay. Yes, no, maybe. Now, the only other part to these is, let's think about, yesterday, what type of graph did we have?
Increasing.
It was x squared, which was increasing, yes? Okay. So when it was increasing, our right, okay, was an over approximation. Yes? For all of them. And then our left, when it was increasing, was an under approximation. And the reason why I specify specifically that it was increasing is because think about if it was decreasing, yes? Or in other words, if our graph was flipped, notice that our rights would be under approximations and our lefts would be over approximations. Yes, so whether it's increasing or decreasing is important in this case. So if it's decreasing, it's an under for my right and an over for our left. What questions do we have there? There's a lot of words for right now. When it comes to it, they're not super hard to find as long as you remember a couple of key things. So let's look at some of the examples. I think those are more helpful than all the words. Alright. So it says over a 12-second interval, a car's speed is never decreasing. And we are given the speed for the following. Okay? We are going to approximate. Total distance. Okay. And we're going to use a left and a right Riemann sum. So the first thing that might be a little bit helpful is we don't necessarily know what exactly our graph is doing, okay? But we do know that it's increasing. So we can put some sort of increasing graph. Which we're not always going to draw the graphs for these whenever we're doing table questions, but for this first time it's a little bit helpful. Now, one really important thing from our tables is we cannot make up values. I cannot use values that are not on my table. That means that I cannot average values that are on my table. I can't look at things just beyond my table, right? I can only use numbers that are directly from my table. We always be there. Which means that, again, we have to look at intervals. So I need a starting and a stopping point, or starting and a stopping x value. So how many intervals could I have from this table? Be careful. So I can go from 0 to 3. I can go from 3 to 6, 6 to 9, and then 9 to 12. So what's the most intervals that I can have? 4. Alright, okay with that. Technically we could do less than that, because I have enough to do like 2, right, or 1. But remember that the more intervals that I have, the more accurate it is. So we want to choose the most intervals that we can do. So for our left, remember that we are choosing the left endpoint to find our heights for each of those. And for our right, we're choosing our right endpoint for each of those. Yes, no, maybe. Okay. So here we're looking that our area is going to equal the sum from I equals 1 to, how many intervals did we say we have this time? 4. So my top number is 4 this time because we have 4 intervals. We can go ahead and make this like an S of x sub I because we are talking about the speed. And then notice, what are my widths of each of those intervals? 3. So we know that our change in x has to equal 3. Are we all okay where I got the setup? once I've figured out what stuff I need, it's pretty straightforward to calculate from there. So again, I'm looking at a left. So my area is going to be approximately, if all of them are being multiplied by 3 and I'm adding them all together, what can I do? Like if I had 3x plus 3y plus 3z plus 3w, huh? I can't divide by 3 because they still have to be multiplied by 3. But I can factor out of 3. That way then I can just do the addition and then multiply by 3 at the end. Yes, no, maybe? Okay. So then for my first interval, we're going from 0 to 3. So what's my x value that is the left of that interval? 0. Yep, not a trick question, it's 0. And then what's our y value, or our speed value that's associated with 0? 30. So that's going to be our first time. Then my next interval would go from 3 to 6. So what's our left x value? 3. And then what's the speed value associated with 3? 37. Okay, so then we're going from 6 to 9. So which y value would I use for that? 45. And then from 9 to 12, we would use 54. And then from there, if you add those all up and multiply by 3, you should get 498 feet. I'm pretty sure that all of us can plug that into our calculator accurately, so I'm not super worried about that. Now, which number for my second one, if I'm doing a right approximation, am I not going to use? The 30, okay? Because now when I go from 0 to 3, I'm using the 37. So I still have 37, still have 45, and I still have 54. But now when I go from 9 to 12, what are we using there? 65 instead. So for our right approximation, we get 603 feet. Which, since we're increasing here, right? Our left approximation should be what? An under approximation. And our right approximation should be an over approximation, which makes sense that then 603 is bigger than our 498. What questions do we have on that one? So far so good. Let's look at another one. This time we're just going to do a left-handed Riemann sum. If you want to draw it out, you can. I don't tend to draw it out if I'm just given a table, just because I think it ends up not being as useful. But if you want to graph it, you can. Again, am I allowed to use any values that are not on my table? No. Okay. So how many intervals am I able to do again? 4. Okay. So I have A equals the sum from I equals 1 to 4. This time I'm looking at an f of x. So I'm going to have f of x sub 1. Now what are my widths this time? Two and 3. Oh, okay. So this time my change in x is not constant. Okay, which is okay. When we have a table, we have to use the information that we're given. So sometimes how much our x value has gone up by is going to be different for each rectangle. And so we're just going to need to adjust what we multiply by. So this time we can't just factor something out because they're different. Now we are using a left-handed one. So from 0 to 2, which of our f of x or y values are we using? 2. Okay. And then what is our width? So that's my first interval. Then from 2 to 5. What are we using there? 3 as my height. And what's our width this time? Also 3. Okay. Then we're going from 5 to 7. What's our height this time? 5. And our width? And then lastly, from 7 to 10. 7 and 3. Questions on that? So if we were to multiply that out, 2 times 2 gives us 4. 3 times 3 gives us 9 plus 10 plus 21. So we get 31 plus 9 gives us 40 plus 4 gives us 44. And we didn't have a unit this time, so it's just 44. Alright, what questions do we have there? Yeah. The second number? Sure. So notice that, what color would I use? Okay, so from here to here is 2, right? So that's where this 2 comes from. Because that's the width of my interval, or that's how much my x is changing. From 2 to 5 is 3. From 5 to 7 it's back to 2, and then from 7 to 10 is 3. So just basically like how much your numbers are changing each time. Or you can just subtract the 2 x values. Either. Now for our last one, they were all 3, and so that's why we just had that 3 in the front. This time, some of them were 2, some of them were 3, which is why we had to like do each of them separately. Other questions? Okay, so this one says use a right-hand Riemann sum to approximate the interval with 6 sub-intervals. So this is kind of our first time seeing an official integral, if you haven't before. So an integral symbol, like I said, kind of looks like an S. The numbers on the top and the bottom are called our bounds. Okay, those are the x values that we are starting and stopping at. So we are starting at x equals 3 and stopping at x equals 9. And the x squared minus 1 is the function that we are using on the inside. So this time, we don't necessarily know what we want our widths to be, but we do want 6 equal subintervals. Alright, so this is our A, this is our B. So to find our change in x, or our width, remember it is B minus A divided by N. So we have 9 minus 3 divided by, and they tell us that we want 6 subintervals. So what do we get? 1. That's nice. We like it when we get 1. Because then we don't even have to multiply by anything at the end. Okay. So that means that what are each of my intervals going to be? Because we're starting at 3. So we're going from 3 to 4, 4 to 5, 5 to 6 to 7, and 8 I'm using 4, 5, 6, 7, 8, and 9. Okay. And remember, how do I find my heights for each of those then? Plug it into our function or our equation, which this time is the inside thing. Yes, no, maybe? So it's still the same process, it just looks a little bit different because they gave it to us in an actual interval. So we plug in 4. 4 squared gives us
16.
minus 1 is
15.
okay. And then again, remember we're adding. 5 squared is minus 1 is 24. 6 squared is
36.
minus 1 gives us
35.
7 squared is
89.
minus 1 gives us
48.
8 squared
64.
minus 1 is
63.
and then lastly 9 squared is
81.
minus 1 is
80.
80. So then if we add all of those together, we should get 265. And that would be our answer there. What questions do we have on that? You don't necessarily have to write them out like this. I just kind of think it's helpful. Like with our table, I draw the little boxes to keep track. Here, I usually do something to kind of indicate what my two intervals are between. That way, then I know which numbers to plug in.